And we'll go from current slide. And before I do anything else, have any of y'all kept up with email recently? Have you seen any message concerning this week? None. Hold on just a moment then. I need to go check on our dilemma. Back on June 12th or sometime like that, Governor Ivey decided that state employees would have Friday off this week as well as Thursday. Well, we don't have school on Friday in the summertime. And the rumor I heard last Thursday when I was over on the Birmingham campus, this is from a secretary, did you hear we're only having half a day on Wednesday? I said, no, I hadn't seen or heard anything. But that sort of makes sense. If the state's going to a 24-hour work week, 3 8-hour days, that would be 24 hours. And we work 10-hour days Monday through Thursday, then 10 and 10 would be 20 and 4 would be 24. So it would be noon on Wednesday. So I hadn't heard anything definite for sure, and even as far as this morning, but I thought maybe they came out with word while I was teaching my first class. So that's what I went down to check. I checked with 2 instructors. They hadn't heard anything. They hadn't talked with the secretary over there that told her anything. So I called my boss, the associate dean, no answer. So I called his secretary, who I heard it from last time, no answer. Well, it went straight to voicemail. So I called his boss, the dean, academic dean, no answer. So I called the executive vice president, got her secretary. They said, no, we haven't heard anything about it. We don't ever hear it until the day of it. Okay. So I called the vice president for academic affairs and got his secretary. And she said, he still hasn't decided yet. I said, I'm in class right now, and I need to tell my students whether to come on Wednesday or not, okay? Well, I'll give you a call. I said, well, I'm going to be in class. I'm in class right now. I'm just coming down there. Well, I'll email you. I'll have Ashley come and let you know. So that's the evening coordinator, and I don't think she's even here yet. So I don't know. I'm just as confused as I was before. I would say check your emails. If you haven't heard anything by Wednesday, I'll be here Wednesday and we'll have class, okay? If I have heard something by Wednesday, you will have seen it on your emails as well. So keep up with your emails. We'll figure to have class unless they say don't. And June 12th, they've had that time to decide, and they still haven't decided what they're going to do with it, And I said, that may be fine for an office worker, but I said my students need to know whether to come or not. Well, that's beside the point. I don't know. I'm so sorry. I can't tell you anything more. I hope to see you on Wednesday, but if I don't, we'll end the class with that then. All right, so I'll fill you in later, okay, in the next class. All right, but yeah, so we don't know I don't know anything more. I'll probably know by the end of class, but I won't be able to tell you then. All right, any questions on anything we've done up till now? Okay, we're in Chapter 8, Integration Techniques and Improper Integrals. And 8.7 is where we finished 8.6 last time. We're just getting ready to start 8.7. Didn't really have time, so we will start right here with 8.7, which is integration by tables and other integration techniques. All right. We'll find an indefinite integral using a table of integrals. And unfortunately, since I don't see but maybe one book and maybe one ebook, 2 ebooks, okay, it's going to be hard for y'all to look at a table, isn't it? So, oh, you got some phones, maybe you can do it there. Okay, we'll find an indefinite integral using reduction formulas. We'll show you how to do that. It'll be in the tables too, but I'll show you how to do that. And we'll find an indefinite integral involving rational functions of sine and cosine. Okay? So that's the objectives of this group, of this section. So integration by tables. I think I probably said it before, but let me re-emphasize it now. We've been learning all these techniques of integration. And out in the real world, most of them will never work. Okay? Occasionally you'll find things that will actually fit the bill and you can do these things. But most of the time, you go to well, I'll take that back. Most of the time, you'll get a package that does the integration for you. Your company, your school, whatever, will have these things, and you'll have the computer do the integration for you. I think that's how things probably work in real life. But before they had those, they had tables, okay? And this, of course, is written for this. Many people find tables of integrals to be a valuable supplement to the integration technique discussed in this chapter. I would say almost irreplaceable substitute supplement. Because a lot of integrals just you can't integrate, or they're things that we haven't discussed here. Tables of common integrals can be found in this text in what they call Appendix B, and I would tell you the page number, except they renumber the appendix starting with A1. So you have to go to the end of the book and find Appendix B, which starts on A3 and goes A through A5 and A6. And this is just a short rendition. Back when I was in college, I was going to say grad school, but it was actually college, one of my physics professors had a deal. He was editor of some big physics journal, and I guess it was published by, anyone ever heard of CRC? Chemical Rubber Company is what it stands for. They used to publish, they may still do, I don't know. They used to publish, I think it was 2 big volumes. The books were, about the size of this, dimension-wise here, probably close to twice as thick, maybe not quite twice as thick. And that had the thinnest paper I have ever seen print on, and it held up. It was incredible how many pages of information they had in there. And they had everything you could possibly want to know about chemistry, physics, math, everything. They're called CRC manuals. I have one down in my office. I just thought about it. I'd have brought it up today. And they had tables of integrals that went incredibly fine print for pages and pages and pages and pages. Differentiation and integration, and tables of logarithms, and tables of just about anything you could imagine you would want a table for. Of course, this is before internet age, okay, well before internet age. So this is how things used to be done. Integration by tables is not a cure-all for all the difficulties that can accompany integration. Using tables of integrals requires considerable thought and insight, and often involves substitution. But even beyond that, not all integrals are integrable even by a table. And each integration formula in Appendix B can be developed using one or more of the techniques to verify several of the formulas. That sort of sounds like a terrible sentence to me. But anyway, they're saying most of these do come from this, but most people will use these rather than going back and saying, okay, is this by parts or, whatever. Now, this is out of that table, and they claim it's Formula 4. Let me confirm that or deny it, one or the other. Looks about right, but I don't have these memorized. Sure, that is exactly what Formula 4 is in the back. And I'm not sure I would call them formulas. I guess that's as good a name as any. But it's they divide these up by different categories. And this one is listed under, they have first 1 and 2 are forms involving u to the n. We all know how to do that. We wouldn't need a table for that. But these are forms involving a plus bu in all of its various forms. And this is the second one listed there, formula 4, is u over a plus bu squared du. Okay. Now, the variable is u, and here you have a u du, and here we have a bu down here. That's not something that looks like it could be done by certainly not use substitution, because you use the variable here, but substitution, possibly a trig substitution. That would be my bet to go to that. No, I'm sorry, partial fractions can be verified using the method of partial fractions. And yeah, that's clearly partial fractions, okay? This one, formula 19, that's probably a trig substitution. No, I'm sorry, this one's by part, because you have a u in the denominator here. Okay, so that would be, 1 over u du would be the derivative of log u, and you could do this with the numerator, okay. So, now, but you'll see that you wind up with an integral form here, which then you would probably use, for this form, a trig substitution, okay? So something like this would first involve integration by parts, and then either another table entry, and then turn around and use a trig substitution for the second part of that. This one, that would just be a simple u substitution problem. So, and you wouldn't need a table for that. You could probably do that much more quickly on your own. But anyway, so most of these do come from some combination of the techniques we've studied, but sometimes it's a juggling act to figure out which one to use best, which one to use first, and to use multiple ones of them. So, but the formulas themselves, you just get them out of the table. Now, they always refer to du, that u could be an x, it could be a t, it could be anything, and they have the letters a's and b's, which you can be square roots or, various fractional forms. So you just have to kind of play it by ear, okay? The book starts with a few simple things to look at. The slideshow did not start with those, so since most of you don't have the books, I guess we won't go. Well, let me just write some of those down, and you see if you can. What if you had this? Let me get my pen set up. Okay, integral of x log x. What would you do for that one? Say again? Just guess something. What does it look like it's set up though? Anybody? Okay, substitution might be worth a shot. I don't think it'll get you anywhere. What would you substitute? Let x u equal log x maybe, and then du would be 1 over x dx. But then I don't think substitution quite would work. So product is what usually comes to mind with that. Say again? I couldn't hear it. Say again?
Split the integral.
Twice? Okay, one more time.
Split the integral. Integral of x plus.
I hear it so bad, I'm not making it.
Split the integral. Like split the integral.
Split the integral. Like multiply?
I guess, yeah.
it almost is like that, but it's not quite, unless this is what you're meaning. Integration by parts, right? Let this be, I would say let this be your U and this be your dV. And that can work, okay? That's an integration by parts. It's a rather strange one because usually you use the more complicated one to be the X, since it's more complicated doing an integration of it, you usually let that be the U, but in this case, you don't have ln to be a dv, so you almost have to go that route, okay? How about this one? Integral of log x over x dx. Substitution, absolutely. Let u equal log x and du is 1 over x, dx. Yeah, so that's substitution for sure, okay? Actually, they say a power rule, which would work too, okay? How about this one? The integral of 1 over x log x dx, okay? Now this to me is rather bizarre because I don't remember anywhere in the book they're using one called the log rule. Do y'all remember a log rule? They say the log rule, okay? But again, I think I would say substitution. Let u equal log x, and then du is 1 over x dx, and then you have 1 over u du. So, but I've never heard of the log rule, okay. But then this one, integral of x over log x. Don't get a headache. None of the techniques we've had will come close to anything like that. This is what they say is not an elementary function. There's nothing that I can think of at all that would work here. Nothing, okay? So, not an elementary function. So, what you would have to do then, I don't even know if that one would be in a log table, okay? Don't believe it will be, but we'll look and see when we get back there. Okay. Now, let's go back to where we were before. Yeah. Now, in ours, and I think most of the tables that have them, that the integrals will be classified according to the form of the integrand. And here are some of the forms listed. The power form, they only have 2 of those. A plus BU, that's one we were just looking at. They'll have several forms under that. And the denominators, numerators of various powers, whatever. Okay? Forms like this that you would have to use completing the square to do, and then probably after you completed the square, use a trig substitution and stuff like that. That would be a classification unto itself, so you wouldn't have to go through all that mess. This is obviously, at least most of the time, either a substitution, depending on what the things are, or a trig substitution at worst. This would probably be a trig substitution, okay? This would be almost definitely a trig substitution, okay? Trig substitution. And then trigonometric functions, those are the multiples of sines, cosines, and things like this, those that we did. Inverse trig functions, yes, I don't remember those. I'm going to the table for those. Exponential functions, a lot of those you can do without going to a table, but when they get really complicated, they will be there too. And then the log functions, especially when you get multiple levels of log functions. Yeah, those will be back there as well. And under the trigonometric functions, those are your simple ones too, sine, cosine, they will be listed too, the very simplest, and then all the various combinations that we might have. Okay, so that's usually how, or something fairly close to that, they have them set up by classes like this. Okay, so here's one. Anyone want to suggest a technique we've used that might work on that?
Substitution.
Don't, say again? Yeah, if that were a binomial, a polynomial there, but with a radical, no. Okay. Yeah, that I thought of that and wondered if there's any way we could make that, but I don't think so. Substitution, I don't think we'll do it either because you have two things in the denominator. The only thing close would be a trig substitution, but it almost has to have a square in it. That needs to be an x squared. So I have a feeling this is one you're just going to have to use the table. Now, and since y'all don't have tables, or at least most of you don't, I'm going to tell you which one to look under. This is not a simple power, so don't do the u to the n. It's not a simple a plus bu. That's well too simple. It's not a quadratic form, so don't try that. It is one that involves square root of a plus bu. Okay? Not quite a plus bu, so let's keep looking. Forms involving a squared plus or minus u squared, nope. But forms of, okay, nope. I think we have to back up and use the one. Yeah, a plus bu. Okay? That is the form I think we'll need. Okay. So you go back to the, going back and forth here, don't lose my place. What's that? 42. On page A5?
Yeah.
Yeah. That has a u squared in it, and we don't have a u squared in this one. So it might make it work, but let me try. If you look at number 17, I think that might do it for you. You just have to rewrite it to be this, to make it look more like 17 in the back. The integral of dx over x times the square root of minus 1 plus x. Now, the only reason I wrote that actually looks worse than the first one, but that's in the form of number 17. Okay? You see, number 17, for those who don't have it, is this one. And I may be wrong on this, but this is what my first guess would be. The integral of 1 over u times the square root of a plus bu du. Okay? So when I rewrote it this way, my a is minus 1, my u is x, and everything else fits. Okay? I wrote the dx on top because that's how they did it, but you could write it over to the side. Well, let's see what their answer is. Well, they have an a greater than 0 and an a less than 0. Our a is obviously less than 0 because our a is minus 1. So we'll take the second form of that, and that would be, I'm going to write it the way they do under 17, 2 over the square root of minus a, because this is for a less than 0, which is exactly what we have. A is minus 1. Okay? 2 over the square root of minus a times the inverse tangent. They write arc tangent, but I just prefer inverse tangent. Okay? Of the square root of a plus bu over minus a plus c. Okay? So let's take that form and apply it to how I rewrote this one. And this would be minus 2 over the square root of minus a minus 1. I'm going to write out all the gory detail here. Oops. There was no minus there. I don't know why the minus showed up there. Okay. Times the inverse tangent. They write arc tangent, but I did that. Of the square root of, and a is a minus 1 plus x, because our b is 1, over a plus 1, a minus 1, okay, plus c. So to clean that up, that would be 2 over 1, okay, square root of 1 is 1. So it's 2 times the inverse tangent of the square root. And I'm going to go back and write it's x minus 1. I don't need it over 1. Square root of x minus 1 plus c. Okay. Let's see if that's what they got in the book. I sure hope so. 2 times the arc tangent of square root of x minus 1 plus c. Yeah. So, the form may not match the form there. You have to be creative but fair about it, rearranging this to make it look as close as possible to what we have there, and then paying attention. Do they have one answer for positive a's and another for negative a's? In this case, they did. We had to choose the negative a one. And, of course, with a being minus 1, that simplified here and here considerably. Okay. So, now, it almost looks like if I had known my inverse tangent derivatives, I should have recognized that one. I'm not sure. Let me go back to the front of the book, see if that even looks. Derivative of inverse tangent is u prime over 1 plus u squared. No, it doesn't look. Oh, but this is a square root, so no, because this is also has a square root in there. So that would have taken quite a bit of creative manipulation to have come up with that. I'm sure you could have some way or another, but it would have required a lot more than what I would be willing to put forth. I'm going to look it up in the table. Okay? Let's see how they did it. I have a feeling it's the same way. Because the expression inside the radical is linear, you should consider the forms involving the square root of a plus bu, which was the third classification, I think, from the previous page. Fourth classification, okay? That linear. If it had been a square in there, yeah, the one that you were talking about would have been the one to go with. Okay? So, this was their formula in 17, but with, and you see they didn't show, you have to rearrange that and put it at minus 1 plus x, and then it looks more like this. But then a is obviously negative, so you have to then go with 17. Excuse me. Sorry. Sorry. What I would call 17b, which is the one with a being less than 0, because negative 1 squared will be less than 0. So this would be 2 over square root of negative 1, which is 1. Arctangent of negative 1 plus this, which I would wrote is x minus 1 over negative 1, which is 1 again. So that's their formula plugging this in with A is -1, B is equal to +1, U is equal to X. Do all that if it's necessary for you, okay? Then plug and chug and see what you get, and that would be 2 times the arctangent of square root of X minus 1 plus C. I'm trying to see if I can at all see the derivative of arctangent in that. It would take a bit of work to get there, but I think it is doable. Okay, any questions? Okay, they're skipping example 2, 3, 2 and 3. So let's go back and we'll try to do 2 and 3. All right, and the second example, if you have, can get to a website, it's at larsoncalculus.com for an interactive version of this type of an example. It says find, sorry, well, that sneezing has loosened everything up. This integral of x times the square root of x to the 4th minus 9. That's a 9. It's an ugly 9, but that's a 9. dx. Okay. Now, go back to the tables and just look at some of the titles. That's not a simple power function. It's not an a plus bu. It's not a quadratic form. It's not a simple square root of a linear form like we just had. Okay. It's a squared plus u plus or minus u squared, but it needs to be in parentheses, in a radical. So the very next one, it says forms involving the square root of u squared plus or minus a squared. So that looks like the section we should be in. Now we see which one. 26 does not have a u in front or an x in front, so that's probably not going to be good. 27 does have an x in front. Okay? Well, a u in front. So here's number 27. The square root is the integral. I don't know. Yeah, that looks like the closest. I'm not sure it'll work, but let's give it a shot. The integral of 27 u squared. The thing that bothers me about this is that doesn't match. I'm going to keep looking for a little bit here. Sorry. That's in the denominator. Maybe 30. No, that's a minus sign. Yeah, that works. No, it doesn't work.
Change of x to the 4th squared and then the 9 to 3 squared.
Right.
And use 32.
Use 32. Only thing is 32.
No, that's the denominator. So
Yeah, I looked at that one too, thinking the same thing, but it's in the denominator.
38. Can you take the square root of u squared?
Most of the one I want to use are in the denominator, and this is really driving me kind of nuts here. Let me try 27 first and see if there's some way we can fiddle with it. But I'm not going to do it too much until I look back and see. No, they say 26. 26. All right. I think what they want you to do is do a substitution first. And let's try that. Let's let
Yes.
all right. Now, I think, well, no, Ricky came in later too. Because I'm liable to forget about it. Once I get into doing this stuff, I'll forget all sorts of things. So let me tell you, since I told the others. Back on June the 12th, or sometime around there, Governor Ivey decided that state employees would have Friday off as well as Thursday. Okay. Now, we're state employees. No one at the college seemed to have noticed that or mentioned it until last Thursday. I heard, oh, because she said that, we're going to be getting Wednesday afternoon off. Because for a 40-hour work week, 5 8-hour days, and if you have Thursday and Friday off, that would be 3 times 8, would be 24 hours. And since we're on a 10-hour work day, 10 and 10 is 20, and 4 would be 24. So the rumor was last Thursday we are getting off noon on Wednesday. Okay. But I hadn't seen anything official. I was in class all morning. I thought maybe they've made a decision this morning, put it out there. So I went down and made phone call after phone call after phone call. Finally, at the vice president's office, they said, we haven't decided yet. So watch your emails, and if you find out school is canceled, closes at noon on Wednesday, if you want to come for a half hour, I'll be here, okay? If you don't, we won't have to do it, but I will be here, I promise you, okay? But if they don't come up with this, or if they say we're getting off at 4 or something like that, then be here, because we'll have our whole class, okay? So watch your emails. I figure they have to tell us sometime. I thought they do it by the day, but no, because they all live in offices, and they don't need to know 2 days in advance. They only need to know the day of. Well, I got to tell my classes, and we don't meet again until Wednesday. They don't understand simple things like that. So let's do a substitution here. Let's let u equal x squared and see what we get. Then du is equal to what? 2x dx. Okay? If you divide by 2, you have u2 over du over 2 is equal to x dx. Now let's plug back in and see what we have. We have a 1/2 out front, and the x dx is going to be a du, and what we have in the parentheses is u squared minus 9, isn't it? Now, you'll notice here you wanted just to have that substitution to deal with that. You didn't want to have to mess around with the minus 9 as part of the substitution. Most of the other substitutions, we would have included everything in there. It might would have still worked, but I think it works better this way. Now we look at this form, and that is precisely a number 26, okay? Because you have u squared minus a squared. So number 26 here is the integral of the square root of u squared plus or minus a squared du is equal to, doesn't make them simple, but I'm going to take some more line than I have to write. So I'm going to write this as a 1/2 Let's see where my parentheses are. Okay, right there. 1/2 of u times the square root of u squared plus or minus a squared. I'm writing down exactly what they have here. When you're doing these, you only use the sign that you need. Plus or minus a squared. No, yeah, a squared log. Still don't have enough room. I'm going to bring my log down here. Absolute value, u plus the square root of u squared plus or minus a squared. Plus c. All right. All right. Now, you see in our problem, the 1/2 is out front. It can stay out front. Okay? Going to be joined by another 1/2 very soon. Okay? The integral then that we got here is simply forget the plus sign and go with the the minus sign only, and the a is equal to 3. Okay? So with that done, that would be 1/2 times 1/2 would be 1/4. Open parentheses. The u is still u. And this will be exactly what we have under here. U squared minus 9. Don't worry about the a squared anymore, or the plus or minus. Just use the minus. And then we use the minus, because whatever the plus or minus was before, we still use the minus. 9, that's your 3 squared, times the log, natural log of u, stays u, plus the square root of u squared minus 9, plus c. But we're not through. Why? Because we have to go back and plug in our substitution. Instead of u, you put x squared. So this will be 1/4 x squared times the square root of x to the 4th minus 9 minus 9 times the log of absolute value x squared plus the square root of x to the 4th minus 9 plus c. I've left off a parentheses a couple of times there. Okay. Now, the only thing that I would be tempted to fiddle with here, and this would take a bit of thought here, are there any, see, this lets me think maybe we can lose the absolute value bar, but we still have the minus sign. Well, this is a principal square root. So we can lose the absolute value bars and just put parentheses here. But that was an x, a u. That u could have been negative, and it could have been enough to overwhelm this. So therefore we don't want to take out this. But with that being x squared and this is a principal square root, we're fine. All we have to do is worry about x's, of course, and this would be in our original problem too. X's have to be greater than, well, x squared minus 9 has to be positive in order to do this. So that means x's have to be beyond root 3 or less than negative root 3. So that's the only thing we have to worry about, and that would go for here too. So we could lose the absolute value bars. Because the x squared can't be negative and the principal square root can't be negative. So let's just make it parentheses, parentheses, parentheses. And that, I think, will do it. I hope that will do it. Let's go back and see how the book did. 1/4 square root, 1/4 times x squared times the square root of x squared minus 9 minus 9 times the log. They've kept the absolute value bars in, which is not necessary. I don't think, no, it's not. Of x squared plus square root of x squared minus 9 plus c. Got it. Any question on that? Yes.
So you could just like move the x.
I'm sorry.
You could just change the x to an x to the negative and move to the denominator, and then use another form, or would that not work?
You can change the x to a minus?
Yeah, the x on the outside of the square root.
Oh, this one?
Yeah. Or you can't do it that way.
Yeah, that is something. Right now I don't think it really matters much, but if you change the problem, then you're probably going to change your solution too. So I don't think what we did before when we flipped the x minus 1 and made it minus 1 plus x, that wasn't changing the problem, it was how it looked. Okay? But to change this and make that a minus x there, that is a different problem. I don't know if it would have a different answer, but I don't see how it would really help you that much. Or did you see some way it would? Are you looking at our book or a different one?
It's a different, like, I have different numbers than yours. It was square root of u squared minus a squared over u.
Over u.
Mm-hmm.
Yeah, you mean x to the minus 1.
Yeah.
Oh, that's a totally different problem.
Okay.
Yeah. And yours probably gave a correct answer, but that's not what this one is. Okay, yeah. I thought you meant the minus 1 as a coefficient, which would be enough of a change, but boy, to put it as an exponent, that is a very different problem. Yeah. So yeah, avoid doing that if at all possible. All right, any other? Good question though. So you see, you might have to adjust what you see to get it to match up with something in the table. And that's exactly what we had to do. Any questions? Other questions? Good question, by the way. All right. Clear? Clear? It sounds like you are or something. Never mind. Okay, so let's erase all that and try example 3. Evaluate this. Now, you can have definite integrals. It's just that you don't have to worry with the plus c. You evaluate between. Okay? So this is the integral from 0 to 2. And most of the tables will not have definite integrals in them. They'll all be indefinite integrals. X over 1 plus e to the minus x squared dx. Now, I have just based on what they just did to us, I have a gut feeling that we're going to have to do something to this one to get it even to a table form. But let's look in the table first and see what we can see. And this will have to go over to the last page in the table, and this is forms involving e to the u. And if you look at this one, I don't see any with a u in the numerator and an e to the minus u squared in a denominator, or really anything very close to that. Okay? The closest it looks like to me would be number 84, but there's no squareds in that. But this is why I was saying I think we need to do some adjusting. Anyone come up with anything we might need to adjust?
Use one of your tricks.
Second?
Use one of your tricks.
Yeah, let's use a trick. What trick?
Take the, let's add and subtract the e to the minus x squared in the numerator. You want to do that?
Up here, you say add and subtract that, and then sounds like a good trick. I hadn't thought of doing that one. All right, I'm going to take out my dx for right now just because it's in the way. but we've got to put it back later. Just don't let me forget to. Okay? So you're saying let's add e to the minus x squared up here, and also subtract an e to the minus x squared up here, and then put your dx. Is that what you're saying?
Yeah.
All right. Now, I think I can kind of see where you're heading on here. This, then you're going to group together and then have a separate integral with that. The only trouble is this is an x and that's a 1. And I'm not sure that's going to help. Yes.
In those e's to the negative x squared, can you move that 2 out in front?
Say that one more time.
For the e to the negative x squared, can you move the 2 out in front, or is that only with logarithms?
The what out in front?
So it's e to the negative x squared.
Right.
Take that 2 from the square and put it in front, or is that only like with logarithms?
Take the 2 here
Yeah.
and move this on. You can do that with a log, but not with that. Okay. I think if what I'm hearing you say,
Yeah.
that's good to do with a log, but not with that connection. Okay. Any other ideas? I'm not saying some of these won't work, but I'm saying I'm not quite equipped to try. You know, because I think it'll take a lot of effort, and you might get it to pan out. Okay. Want me to go back and come up with a suggestion of my own? And so let's, for right now, though it sounded like a good idea, we might come back and check and see if Bill's will work. But here's what I would say first. Y'all have heard of KISS, haven't you? You know what it stands for? Oh. Yeah, keep it simple, stupid. Okay, never mind. I guess that's an older generation. Maybe we only know that one. Let's just try this. And this is sort of based on the last one. Let u equal minus x squared. Okay? That's the offending thing here. And the fact that my numerator is coming close to being the derivative of that, that's what leads me to do that. What would be my next step? du is equal to negative 2x dx. All we have to do is divide out a minus 2 here, and we have our numerator. So I'm going to bring my dx back in a little closer. Okay, and let's see what we've got here. Okay, I see something I really don't like here. But let's see what we've got. I'm going to leave the units off, the limits off for now. So what we have is a minus 1/2. That takes care of that. Du, which is your x dx, over 1 plus e to the u. Don't we? The problem here is this. Those limits. Usually like doing this, but we're going to have to say, yeah, let's divide by minus 1. So we'll say minus u is equal to x squared, which then leads to x equal plus or minus the square root of minus u, which is really a pain in the neck. That's what really bugs me here. Can we just settle on the positive, or do we have to consider both? This is really bad. So when x is equal to 0, I think it's pretty clear that u has to be 0 no matter what we do. I don't know. We didn't need to do all that, did we? Let's take all that back. I'm sorry, I was making it more complicated. I was not keeping it simple, was I? Okay. When you plug in 0 for x, you get a 0 for u, and when you plug in a 2 for x, you get a -4 for u, which really isn't all that bad because you got that minus sign out in front. So this is going to be 1/2 the integral from -4 to 0, because flipping the units, the limits, negates the thing, and then it would be du over 1 plus e to the u. Now, I bet you that one's in a table, and I hope not to lose the bet, okay? Forms involving e to the u, look at number 84. That is it almost verbatim. Okay, and for some reason, oh, here they are. I've lost my marker pages. Number 84 is almost that completely. What we have then is this thing is equal to 1/2. Now this time I put a bracket here and I put what they do here. U minus the log of 1 plus e to the u and I don't put the plus c because I close out what was my bracket and go from -4 to 0. Alright, so let's do that. That'd be 1/2. I'll plug in a 0, that's 0. Minus the log of 1 plus u to the 0 is 1, so it's minus log 2, I think. Y'all correct me if I'm wrong. Yeah. Okay. Then minus a minus u, which will be a +4. Minus a minus is a plus. The log of 1 plus e to the -4. And frankly, I'm pretty happy with that as an answer. I guess you could make it 1/2 4 plus the log of 1 plus e to the -4 over 2. That might make it a little simpler. I don't know if it's... Yeah. And they may actually come up with a number, and they actually do. So they did 1/2 the log of, and they didn't do the division, log of 1 plus e to the -4 minus the log of 2. So they must have had a calculator on them, which I don't. So if you'll do that, 1/2 of, they put it in this order, 4 plus this minus that. See if you get what they did. I wrote it in this form, but they didn't. They wrote it in this plus this minus that. That's what they did. Same units, they just put them in different places. And again, I'll get on one of my favorite griping points and say, yes, and if you have been doing this in WebAssign, and you didn't put that in the order they wanted to, they just said it was a wrong answer. Or if you put it in a form that was a little bit different, they would have definitely said it was the wrong answer. Where it would have been a wrong answer, it would just not been in the form they put it in. So I don't, that's what sort of bugs me about WebAssign, as you may have told by now. Okay. Ooh, no, 1.66. Did you? I don't know how you get there from there, but see, 1/2 of 3.66 would be 1.33. So that would no, that may be right. Did you do the 1/2 in front? You did. Okay. Okay, do this one, not the one I did. 1/2 of 4, open parentheses 4, plus log of 1 plus e to the minus 4. Close that off. Minus log 2. See what you get. I haven't done it, so they may be wrong in the book. I don't know.
I got 0.66.
0.66. Okay, split the difference, you get 1.6. I'm just kidding. Okay. Yeah. Okay. But anyway, they say it's 1.66, approximately equal to. Now, they also show it's almost a triangle. I would never have guessed that graph would have come up. Mess up my pen. To be that, which you could estimate by being that would be awfully close to a 2 by 2 square would have been 4, and half of that would have been 2. And this is 1.66. So at least if the graph is right, that answer is probably not far off, because there is a little dip there that would be exactly the bisecting triangle. So I would say if their graph's right, their answer's probably right.
I plugged it in.
Okay. Huh?
I plugged it in again and got
1.66. Okay, good. That just reminds you to plug it in 3 times. No, I'm not. Okay. All right. Now let's go to reduction. Any questions on using the tables? They're not particularly easy until you get it into a form where they are easy. And it takes some creativity, imagination, luck, tricks, or other things to get it into the form where it would be reasonable. Okay. All right, to erase. I should, I guess, write down. This is approximately, ooh. For some reason, my pen disappeared on me, and it still disappeared on me. There we go. Approximately 1.66, since we have kind of confirmed it. Okay. So let's move on to reduction formulas. Several of the integrals in the integration tables have the form of this. The integral of some function here is equal to some other function plus the integral of some different function. Now this almost reminds you a little bit of an integration by parts, where you're integrating something by parts and you have something that's not in an integral, usually minus something that is in there. But this is yet something different from that. Such integration formulas are called reduction formulas because usually this is a simpler form than this was. Okay? If it's not, why did they do that? Okay? Because we reduce a given integral to the sum of a function and a simpler integral. So you want that to be a little bit simpler. Okay? Oh. All right. Thank you so much. All right, here it is, fresh off the presses, sent, well, I don't have much, less than 15 minutes ago. Due to the fact that Governor Ivey is recognizing July 5th as part of the July 4th weekend, the college will close on Wednesday, July 3rd at 12 o'clock noon. Okay, sorry about that, folks. Wait, pull out the hankies. This is a sad time, isn't it? Okay. This means we have a 24 clock hours of work for staff Therefore, on today we're working 10 hours as if that's something new. Tuesday we'll work 10 hours as if that's something new. I usually work more than that both those days. And on Wednesday we'll work 4 hours. All classes beginning at 12 p.m. on Wednesday and all Saturday classes will be canceled. We will resume regular classes on Monday, July 8th at the normal times. Are any of you in any of the A&M classes that meet here on this campus? Okay. And that one. So, happy 4th of July. So, I will be here at 11:30. If any of you are here, we'll have 30 minutes of class, okay? If you don't want to bother making a trip out here for that, I understand. And we probably won't have 30 minutes of class, but if anyone's here, we will. But it'll all be recorded, and y'all will be able to pick up on it. So do whatever seems best. I will be here at least until 12 noon. So it's not that I will be going anywhere, but it seems a little crazy, especially if this is your only class. Now, I'm going to pause this for a moment here because it's time. So anyway, these are reduction formulas if you do lead to a simpler integral. Now, the other thing about them is usually the integrals are related to each other somehow. Of course, they're part of the answer. But what I mean by that is that this integral is usually a lot like this one, but in maybe smaller exponents or something like that. So you can do this repeatedly, keep reducing until you get down to something that is doable. Okay? And I'm pretty sure they're going to give us some examples of that. Okay. Here's one. Find the integral of x cubed sine x dx. Now, this one, definitely, we could use one of our techniques. I say that, I'm pretty certain it's the case. What technique would work? Parts. Integration by parts will do. Let u equal x cubed, du equal sine x dx, and just keep going at it until you get down to something you got. Okay? Now, that didn't make a lot of sense, did it? But hopefully you understood what I meant. Now, what we'll do with this one is go back to the back of the book, to your table, and what we're looking for are ones that involve trig functions, sines and cosines. Okay? And their number 54 on page A5 looks like it's the deal. Its form is the integral of u to the n sine u du. And they get this from integration by parts. I'm basically would bet you that, okay? Minus u to the n cosine u is exactly plus n. Now remember, n is not what you're integrating. N is just a number. That's that first power. Times the integral of u to the n minus 1 cosine u du. Okay? Now, notice with these, they don't usually put a plus c, because you don't need to put the plus c till you get to the last integral, and then put it in. So let's do exactly what they say here, and what would this be? You tell me what to write. Negative x to the third cosine x plus, so I get 3 times the integral x to the squared cosine x dx. But ooh yuck, I don't know what to do with that one. Or do we? Let's look at forms involving sine u and cosine u, and look right across the page, not right across, yeah, the same page, let's right across and see what number 53 says. Number 53 says that the integral of u cosine u du is equal to cosine u. Wait a minute. I'm sorry, 55. Integral of u to the n, cosine u du is equal to u to the n, sine u, I don't know, I was looking, my eyes went to the wrong line. Sine u minus n times the integral of u to the n minus 1 sine u du. So, now I'm going to jump down here and hang on to my first term, minus x cubed cosine x plus 3 times, and instead of x to the n cosine x, we want to put what this one is. Okay? And what is that one? X squared sine x. Yeah, wait. Okay, minus, what you say, 2? X sine x dx. I get to writing faster than I'm thinking or talking or something. Oh, it's not erasing. All right. Okay. Now we go up to number 52, the integral of x of u sine u du, and we can just write that one down. So I should have not skipped as much space there, but I'll do it here. So our final, I think it's going to be our final answer, it's going to be the x cubed, or that's, yeah, minus x cubed cosine x plus 3 x squared sine x minus 6, 3 times 2 is 6, times what number 52 tells us. Sine x minus x cosine x plus c. All right, so let's write down our final after clearing that last set of parentheses. Minus x cubed cosine x plus 3x squared sine x minus 6 sine x minus 6 x cosine x plus c. All right, let's see if we can come up with a, see what they got. Oops. All right. Example 4. Well, we're going to see what they got, but let's, before I erase it. Minus x cubed cosine x plus 3x squared sine x. They got a plus. Oh, yeah, this is a plus. Minus here, minus, okay. Plus 6x cosine x minus 6 sine x plus c. And if you had written these, I don't know why they wrote the others in the order they did, but the way they did it, let me do that. Minus x cubed cosine x plus 3x squared sine x plus 6x cosine x minus 6 sine x plus c. Okay. Now, it's not something that you can bet the farm on, but notice the pattern here. Your x's are going down in power, x cubed, x squared, x to the first, x to the 0. Your trig functions are minus cosine, plus sine, plus cosine, minus sine. And then you got your plus c. And if you think about your trig functions, because derivative of minus cosine is positive sine, derivative of positive sine is positive cosine, derivative of positive cosine is minus sine. So that takes into account your sign changes there, SIGN changes. The coefficients are not quite so clear, except it was outside your thing was a 3, then a 2, and then would have been a 1. So the last would have been 3 times 2 times 1. So this is 3, 3 times 2, 3 times 2 times 1. That's what happened to your coefficients there. So again, nothing to bet the farm on, but that's the pattern that's set up here, especially if you rearrange those terms with what they did. And it looks like, at least it makes pretty reasonable sense. All done by integration by parts, okay? And you could have gotten that same answer. It would have taken a little more work, but this was plenty of work, okay? I'm not going to gripe that this wasn't work enough, okay? Now, that was let's see how they do example 4. So let's erase all this. I think it's probably going to be awfully close to the same thing, but let's just see. Consider the 3 formulas listed below. Here's formula 52, which we used. I think it was. I was thinking that. No, it was 54. They got the number wrong. Okay. In our book, that's 54. Now, maybe they added 2 more somewhere that I don't know about, but that's 54 in our book. Okay. No, it isn't. Sorry. 52. They're doing it in reverse order. That is 52. U sine U, U to the n sine U, that's 54, and U to the n cosine U, which is 55. But we did them in order of 54, 55, 52. They put them in order that you see them in the book, which makes really no good sense at all. But it's okay. Using 54, then 55, then 52, the x cubed sine x dx would be minus x cubed cosine x plus 3 times the integral of x squared cosine x dx, just like we did. Okay, and then using 55 next, we'll do x cubed cosine x plus 3 times, and then 55 gives us x squared sine x minus 2 x sine x. And then 52 on that last one would have been copying this one down and then multiplying through it. This would be plus 3x squared sine x. And they skipped some steps here. It would have been a minus again. X cosine x. So plus 3 minus 2 times a minus would be a plus 6 x cosine x. Then a plus 3 minus 2 times sine would be a minus 6 sine x plus 6. So that is what we got. They just skipped a lot of steps that got us there. But that's exactly the answer we got. All right. Now, they're skipping example 5. So let's go back and pick up example 5, which I guess let's go back another slide or two, right there. That'll give us more room. Okay. We've just gone past the midpoint, haven't we? Are y'all okay to just keep trucking, or? Okay. If anyone needs a break, let me know. These are long classes, and bladders will only take, whatever. Okay, so let's do example 5. Find the integral. And by the way, if you haven't noticed it, on the slide set, they show you the easy ones, and then on the ones that are not as easy, they don't show you how to do those. So I have a feeling this is going to be a little more challenging than the one we just did. But I don't know that for sure. The square root of 3 minus 5x divided by 2x dx. Well, that's pretty ugly writing, but except for that, where might we go? It's nothing that comes directly to mind here. Normally, say in a substitution, you try to find the innermost part, the most complicated look at the part of the problem. But on the one hand, that would be it. But on the other hand, this would be it. So we've got competing difficult parts of the problem. So probably a substitution is not going to be all that effective here. Maybe Bill can come up with one of his tricks that might help, because I was thinking something like that might work here. But let's go back to the tables and see. Now this is a linear form, sort of like we did in our very first problem, the square root of a plus b squared. Now a plus bu. Okay? But in this case, the b is negative. So we may have to do a little bit of fiddling with that. Now, number 16, both the u and the integral and the radical are on top. We've got the u on the bottom and the radical on top. Number 17 has both of them on the bottom. We have the one on the bottom, the other on the top. And 18 is a power on the bottom with the radical on the bottom. Ha! But look at number 19. Number 19 looks like it might be close, because you have the radical on top and the variable on the bottom. The trouble is the b, okay? It's not the right b, is it? All right, so how are we going to manipulate that? So let's come over here to the side and write down what they've got. Number 19 in the back is the integral of the square root of a plus bu over u du. Okay. It's really not going to be as far off as what you might think. Okay? Now, how do we get ours to look like this? Well, our a is obviously going to be 3. Everybody agree? Our b, hopefully you see, has got to be a negative 5. Hopefully that won't be a problem. But how about that 2x in the denominator? Problem or not? Not really. Make it a 1/2 the integral of the square root of 3 minus 5x over x dx. That wasn't that big of a problem, was it? All right, just pull that constant out here. Okay. And get that writing off the screen. Okay. Now I think we're probably ready to go for it. So let's write down what this answer is in terms of a's and b's, and then we'll plug in our a and a b up here. This will be a 19 is what I said, right? Yeah. This will be a 2 times the square root of a plus bu, okay, plus a big boo hiss here because we have a reduction formula, times the integral of 1 over u onto the square root of a plus bu du. Now, I don't know about you, but to me that looks worse than the first one did. Okay? Because now you got both of them in the denominator. Okay? But if you look at that, because that looks sort of familiar, turn back one page, and number 17 gives you an exact answer for that one. Okay? Or at least two exact answers for that one. One if A is positive and one if A is negative. Well, our A is 3, that's the positive one, so that's the one we're going to use. Okay? So rather than write that down, I'm just going to write down our answer for this one. Okay? So, or you tell me what to write. I'll start off with the 1/2. I'll tell you that part. Okay? Now, we're using this form, which is that is the answer to. All right? Obviously, there's a 2 there, right? Times the square root of 3 minus 5x. You don't have to really stop and think about this. This form, that form, that form, they always are in the same form. So just write what's in the radical as the radical. Okay? That's hunky-dory. Okay? Plus a is 3. And now we do the integral of, wait, maybe I should write that one down so I don't have to write it twice. So let's just do what this one is, going back to the previous page, number 17, and with a positive, this will be 1 over the square root of a times the log of absolute value, square root of a plus bu, minus the square root of a over the square root of a plus bu plus the square root of a. I hope I'm looking at the right one. And then we'll have our plus c. All right. So we've got the c part done. The c, that's the a. And then we have 1 over root a. So, let's see. So I don't need the integral sign anymore. Now, here's the thing to watch, folks. Because, okay, it'll really sneak up there and bite you where you don't want to be bit. And this will be all these brackets. Okay? I'm going to take out this one. Okay, because you see you got a bracket in front of this one because of the 1/2 there. And then you got your 3 here, and then you got a bracket in front of that one. I probably should use a different symbol, but I'm not. And then we got a 1 over a, because this integral here is exactly that, but your a is 3, so it's 1 over the square root of 3, okay, times the log of absolute value of, but here's where the beauty comes back. That radical is exactly this radical, so it's the square root of 3 minus 5x. Okay? Minus, and your a is root 3, the square root, your a is 3, So it's minus root 3 over that same radical, 3 minus 5x. I can't write. That's really ugly. Okay. Plus root 3. Plus c. Because this did not have a limits on it. Okay. Now, you got to close this bracket and the next bracket. All right, let's see if we can take care of our coefficients without screwing something up. 1/2 of 2, I think I can do that one. This is the square root of 3 minus 5x. Okay? Plus. Now, before I multiply by 1/2 of root 3, let's do the root 3 over 3 over root 3, which is exactly what? 3 divided by root 3. Oh, y'all know that, don't you? Root 3. Because root 3 is root 3 times root 3. And if you do root 3 times root 3 divided by root 3, you just get a root 3. And then you got the 2, so this is root 3 over 2. That's this one times that one times that one. Times the log of absolute value of square root of 3 minus 5x. Okay. Minus root 3 over the square root of 3 minus 5x plus root 3 plus c. Oops. All right. I'm hoping that's their answer. Let's see if it is. Example 5. Root 3 minus 5x, got it, plus root 3 over 2 times the log of root 3 minus 5x minus root 3 over root 3 minus 5x plus root 3. Oops. That's an absolute value bar plus c. All right. Now, interesting thing to note here, the sign of b was not an issue anywhere here. A, it was. I mean, which one we use of this reduction? Come back. I didn't mean it. There we go. Okay. What? Have I got some sort of magnetic field here when I get too far away? When I get close, it's fine. When I wheel over here, okay. Yeah, the sign of A mattered here. I've already erased it, I guess. I thought I had it somewhere here. The sign of A mattered on which one of these reduction formulas you use, but A was positive. The sign of B never entered the picture here, so it just carried through. Every time you saw square root of A plus BU, it became square root of 3 minus 5x. It didn't really matter what the sign of B was. It did matter what the sign of A and which reduction formula you use, or which one of the things, but it came into play there, but not else. So with A being positive, addition 1 didn't have to change any signs. So the first reduction formula has a reduction in it, getting you to a form that actually looks worse but has a final answer, which you don't have to reduce any further. So that kind of stuff. Any questions on that? Fortunately, they didn't show us a graph of that one. All right. No questions? Hanging in there well, huh? Okay. All right. Next, we're moving to rational functions of sines and cosine. Okay? Now, here's example 6. find the sine of 2x over 2 plus cosine x dx. Now, I haven't looked back at the table yet, but I bet you there's nothing really close to that in the back, because they don't mess around with different arguments on your sine and cosine. So anyone want to make a guess of what we might need to do first?
Can you split it?
Okay, what do you mean by that? I've had another splitting headache. No, splitting thing that I didn't know what it meant. Okay, what?
Never mind.
No, what were you thinking? What were you going to split?
Well, I forgot, like, if the rule is, like, you have it divided, you cannot split it into two variables. Can you do that? I don't think I know what I'm talking about.
Yeah.
Never mind.
I'm not too certain on that, okay? But someone give me a first step. What's the biggest problem you see here?
Expand sine of 2x.
Yes, and get it into terms of,
2 cosine sine x.
that's exactly it. They don't deal with two different arguments of your trig functions. So get it into one argument, which is just your x, by the double angle formula, and that would be, as Bill said, 2 times sine x cosine x, I just put the 2 on the outside, dx over 2 plus cosine x. Okay. Now, somehow in the pit of my stomach, I don't feel like they're going to have that form in the back of the book either. Okay? So what? They might. Maybe they will. Can you think of anything else you might try? Okay, what would you substitute?
2 plus cosine x.
That would be my, if I were going to substitute, that would be what I would try. So let's see what happens if you do that. You want u, that's everybody's favorite. Okay, let u equal 2 plus cosine x. Okay, then, next step, du is equal to sine x dx. Okay, with one little exception. No, negative. Derivative of cosine is negative sine. Okay, that was the exception. Not going to do anything else. Okay, now, I would come back up here and say this tells us that cosine x is equal to u minus 2. Right? Okay, this may be a trick, Bill. I'm not sure it is or not. Let's see what we've got. We've got 2 times the integral. Oh, let's do minus du is equal to sine x dx. Okay, so let's pull a minus out too. And we have u minus 2 du, because sine x dx is minus du. We already pulled the minus out. And cosine x was u minus 2. So I think that covers the numerator over u. Who needs a table? This is fairly easy to work out, isn't it? It's a minus 2, and there weren't any limits on this. And this, I would split, if that's the right term for it, and say the integral u over u is 1 du and then minus a minus is going to be a plus 4 times the integral of du over u, which is minus 2 the antiderivative of du. It's just u, right? Okay. And then this one would be plus 4, and what was that one? Du over u? That's the log u. Okay. I'll put it in absolute value bars here, and then we'll put a plus c at the end. Now let's go back and plug in what u is, or u are, or whatever, is 2 plus cosine x. That would be a minus 2 times 2 plus cosine x plus 4 times the log of, and here I think we do need to keep the absolute value bars, 2 plus, no we don't. Why don't we need absolute value bars on that one? Because cosine is never any less than minus 1. So minus 1 plus 2 is going to be a plus 1. So that's always going to be positive. The 2 plus cosine x is always going to be positive. Okay? So I think I'd write this answer as 4 log 2 plus cosine x minus 2, no, minus 4. Let's go and multiply through. Minus 4, yuck, minus 2 cosine x plus c. That seemed way too simple. See what they got. Minus 2 cosine x plus 4 times log of 2 cosine x. And they just incorporated the plus 4 into the c, or the minus 4 into the c, because it's just a constant. So it doesn't seem fair, but they did. They just combined minus 4 plus c and made it a new constant, plus c, or whatever. So, but yeah, that's exactly the answer they got here. Minus 2 cosine x plus 4 log of 2, and they didn't have to put absolute value bars there, plus c. Now, they said that was in a table, so let's go back and see if it was. Oh, they used the A plus BU form. And frankly, that was harder than doing what we did. So don't use the table if it doesn't help you. I mean, by all means. We got the same answer, I think, a little simpler than they did. Because they're sort of complicated the way they did. Any questions on that? Well, let's just, this is on here, so let's watch how they did it. And you decide whether you like it better or not. First step was, though, the same. Any questions before I erase it? Okay. So you can't use two different arguments, so go on and get your double angle formula. And like I said, pull the 2 out, and that'd be sine x cosine x over 2 plus cosine x dx. Now, a check of the forms involved, and like I said, you're not going to find that in the back. I would have been shocked to have found something like that in the back. A sine u or cosine u in appendix B, you don't have them mixed up like that. So what they did was, partly like we did, but part not, they skipped a bunch of steps and said, use this form. Well, how do you use that form? Well, they said, to do it the way they did, they would have just said, let u be cosine x. Okay? And then du would have been minus sine x dx. So then this would have been a minus 2 cosine x over 2 plus cosine x dx. And then like that is in this form. You have cosine x, a plus cosine x down here. Where your a was 2 and your b was 1. And then looking that up in the table, you came up with this. And that would have been just b times u minus a over b squared times log of a plus bu, then plus c, the formula 3. And plugging in a is equal to 2, b is equal to 1, u is equal to cosine x, then you get 2, that was out there, and we already did that, minus 2 times that. I don't know why they're going back and redoing that again, but they did. And then this would have been your u minus 2 is there, u minus 2 log of this thing, 2 plus cosine x. So you don't need the absolute value bars, plus c. And then plugging in, you get minus 2 cosine x plus 4, minus 2 times minus 2 is plus 4 log 2 plus cosine x plus c. Okay. Now, I don't know. It just seems like to me their method included a lot of skipping steps and insight. This can be written this way and you can do it that way there. Whereas the way we did it was a simple substitution. You could, it was really easy to do that without going to the thing. So, if it works, do it. For integrals involving rational functions of sine and cosine, here's the substitution. Oh my word. U is equal to sine x over 1 plus cosine x is the same as tangent of x over 2. Of course we remember that from our half-angle formulas, don't we? I'm not even sure that's in the front of the book, but let's see if it is. They have a page on trigonometry. They have double angle formulas, but they don't have the half angle formulas. And they're saying just use this substitution, which is not one that I would just come up with in probably 1,000 years or so. But let me show you basically, I'll try to show you basically where they got it. Not sure I'm going to do a very satisfactory job of it, or y'all may not even care, do you? You do. Okay, let's try it. First thing I would try to do would be this, and this may not yield us anything. Multiply numerator and denominator 1 minus cosine x. I'm not sure this is going to get us there, but let's try it. Okay, just doing that part. we get sine x times 1 minus cosine x over 1 minus cosine squared x. By that, and 1 minus cosine squared x, so is what? Isn't that sine squared x? Pythagorean identity. And then do that out, and you get I think you got to use your half angle formula somewhere here, and it really irks me they don't give it to you. Because this isn't going anywhere fast. 1 over sine x would be cosecant x minus cotangent x. Because cosine over sine would be that. But that still doesn't give you tangent x over 2. And I've got to go back and reformulate the half angle formulas that involves yeah, it really isn't. I mean, what you have to do to get the half angle formulas, that this didn't do us any good, so I'm going, whoops, that's not what I wanted. Okay. I wanted to erase all that because that didn't get us anywhere. I'm going to try this one. I don't know if it's going to work. It doesn't look like it would. The tangent of 2u is equal to twice the tangent of u over 1 minus tangent squared u. That doesn't look like it's taking us anywhere useful either. Goodness, I wish I could remember my half angle formulas.
I think I go back to double angle formula.
Yeah.
We can get at least the sine of A is equal to square root of 1 minus the cosine of 2A divided by 2. Start with sine squared and comes out 1 minus cosine of 2 times sine of A or whatever. And then take the square root of the sine of A.
Yeah, it has square roots in it, but the sine and cosine do, but the tangent doesn't. And because it's a ratio of the two, and I'm sure this is what it turns out being, but getting it to go the other way, I think this is, and this is probably what you're saying. If you go this route, cosine this probably is what you're saying. Cosine of 2u is equal to 2 times the cosine squared of u minus 1. Okay? Right? And then solve this for cosine squared, and you have cosine 2u plus 1 is equal to 2 cosine squared u, and then divide both sides by 2, and then take a square root. So cosine u is equal to the square root. I think they usually write it as 1 plus cosine 2u over 2. Okay, but then change it and make this cosine x over 2 is equal to the square root of 1 plus cosine x over 2. So that would be your cosine half angle formula. Now, do the same type of thing with the sine. Okay. And the sine cosine 2u is equal to 1 minus 2 sine squared u. Why is my pen not writing? Every now and then it just clinks out on me, and I don't know why. Okay. It's kind of lost its mind here. I can't get it to do. Okay, maybe it'll do something now. Nope. It seems to have quit working. I don't know if you can see it. Oh, you can't. Oh, it disappeared. Try it again. Oh, no. Yeah. Well, it disappeared again. Okay. That right there that disappeared, right over the 5, that's my cursor. I'm clicking on this, and it's showing up here. And it won't click. And if I could go further down on the page, okay, maybe it did something then. Now I'm getting that thing. If it doesn't stop doing this in a bit, it's Microsoft PowerPoint, of course. What would you say? Restart, close, or wait for it to respond? Give me an idea.
You can wait for it to respond.
Okay.
Or you can close it and open it again.
What's that?
You could close it and open it again, but
I still couldn't hear.
we'll wait for it.
Oh, okay. It just sometimes loses its mind, and I don't know what to do with it. What I think I'll do is go and write it. Poor people at home won't be able to see it, but I'll try to write it out here. This is 1 minus 2 sine squared u. Right. Okay. Solve this for sine, so that would be 2 sine squared u is equal to 1 minus cosine 2u, divide both sides by 2, and then take a square root. Let's come down here and do it maybe. So sine, now I'm also going to change the u to u over 2, or x over 2 like I did before, is equal to the square root of 1 minus cosine u over 2. So here we have the cosine x over 2, the half angle formula is the square root of 1 plus cosine x. That's supposed to be an x. Okay. Cosine x over 2, and here sine x over 2 is equal to this. So, if I do the ratio of these two, is it still doing its thing? I don't see the, yeah, there it is. Okay, it's still doing it. I don't think it's doing anything. But then if you do sine x over 2 over cosine x over 2, that's equal to tangent x over 2, and that's where you get sine over cosine, and the square root of, so you get this one on top, 1 minus cosine x over 1 plus cosine x. Okay. Now, I think that's right because the root over the root 2's are going to cancel out. Okay. Now, if you multiply this one by 1 plus cosine x, I hope I'm doing the right one, and this one by 1 plus cosine x, then this gives you 1 minus cosine squared, which is sine squared, x, and this gives you 1 plus cosine squared x. Okay. Now that's not very useful. No, 1 plus cosine squared x squared, so basically you can lose the square root and the square here, and that gives you that form. If you had done the minus here and minus here, then that would have given you 1 minus cosine x squared, and then the square root loses that over sine squared, and the square root of that would be this.
But didn't you already have it?
And that's exactly what we had before. This was cosec x minus cotangent x. So yeah, that's exactly this form right here. This one,
Yeah.
yeah, without the square root. That's all about that. 1 plus cosine. Yeah. So yeah, that is exactly that form there. So that's where that comes from. Okay. If you wanted to know why that's true, this is why it's true. Now, you want to keep letting it run, or see if we can end it? Okay, I'm all in favor. Let me see what happens if I do this again. Close the program, restart the program.
I would probably just close it.
Close it? Okay, we'll close it. Microsoft PowerPoint is not responding. Surprise, surprise. It's a really lousy package in my mind, but I'm biased. I really don't like anything Microsoft. Okay, so we go back to 8.7 is where we are. Okay. Now, you, all that mess we just did, people at home won't be able to follow it because, well, I said it, but I didn't. It won't be projected. So let me get it off the board here. But we basically got that form that we had there. That was where they magically said, oh, this is it. Okay? So that's where it came from. Now, I don't remember where we were. Beyond that, beyond that, beyond that, beyond that, beyond that, beyond that. That's it. From current slide. Okay. So that gave us this part. So we verified that is indeed true, for what that's worth. Now, so let's fiddle with this a little bit and square that. Okay, let me get my pen back. So u squared is equal to sine squared x over 1 plus cosine x squared. Okay? Now, all right. Now, let's is that the way we really want to go? I guess so. And 1 minus u squared would be 1 plus cosine x squared over 1 plus cosine x squared minus sine squared over cosine x plus 1 squared. I just wrote it differently because I messed up. Okay. All right. This is a hard way to do it, but basically, if you went backwards the way we just did, you'd come back up with these things, but I really don't know if I want to reinvent the wheel and do all that. But let's see what happens when we do 1 plus u squared would then be 1 plus cosine x squared over 1 plus cosine x squared plus sine squared x. I left off my x here, didn't I? Over 1 plus cosine x squared. Okay. And if you divide it, losing my voice here, divided those, like they say to do here, notice your denominators wipe out. And what you have then is 1 plus cosine x squared minus sine squared x over 1 plus cosine x squared plus sine squared x. Oh, man. And if you squared this, it would be 1 plus 2 cosine x plus cosine squared x minus sine squared x over 1 plus 2 cosine x plus cosine squared x plus sine squared x. Well, certainly that equals 1. Okay. So this would give, I don't know why it matters, but I don't know. It's just going to take more time than it's worth to do. But these are indeed true formulas. if you go back to the form we had before this, when it was a lot simpler, and I wish we had that now. Oh, I left some of that up there. Let's try it this way. U squared would be tangent squared x over 2. Maybe that would have been easier. 1 minus that, would then, and then 1 plus that. Yeah, that probably would have taken us back to where we needed to go, and it's sort of like the half angle formula is going back to the double angle formula. Let me try. I don't know. Is it worth it to prove these things? I know it's provable. The question is it worth it? I'm not certain. If we did this, let's try it this way. 1 plus cosine x is equal to sine x over u. I don't think that's worth it either. And then subtract 1 from both sides. Make it u over u. So sine x minus u over u is equal to cosine x. And then plug in that for u. That doesn't seem fair, but nah. I think we just have to sort of take the word for it for right now. Wait, let me just erase it off. But if you went back through what we just did, we almost had that very form before we did the half angle formulas. If you think about it, when I wrote those, oh, I kept thinking, why isn't that erased? So that's because it's here. If you think about the sine squared u was this form, and cosine squared u was 1 plus cosine 2u over u. And when you well, I don't know. I don't think it's worthwhile. We're just going to be using these. You could square these and fiddle with them until you got them into this form. It would be a lot of work, but you could do it, eliminating the sines with, into cosines or the cosines into sines, and you would get these. But then, if you take, boy, did they ever, I mean, that almost looks like mystery meat there. Well, maybe I mean, it really looks like they just pull them out of the air. I can see where that comes from, but for the life of me, I cannot see exactly how they got there from either one of these. This looks like it might be the easier one to do. D sine u would be cosine u du. I mean, derivative of this would be cosine x dx. And then you still have these are just special substitution to convert trigonometric expressions to standard rational expression. And for now, let's just take the word for it because we're running out of time. And I think it would take most of the rest of the time just to get these. And I'm sure there's an easier way to do it than what I was just doing it. I think if you go back to what Bill suggested, the half-angle formulas would get us there as well. Do you see an easy way to do that right off the top? And then I especially don't see where this one comes from. I'm sure it's right. They wouldn't have put it in the book if it wasn't. But boy, that just seems to be pulled right out of the air. You could do the du here and then manipulate this, but that would be in terms of sines and cosines. They've got the dx here, where if you take a derivative of either one of these, you still got a sine or a cosine to fiddle with, and then using these to plug back in, perhaps you do come down to something that simple. But boy, that is not trivial. That's, well, they show a little proof here. And they did exactly the way I was starting to do it, but with perhaps a little more elegance. Okay. I'm sorry, if I just looked in the book, it would have been here. Do exactly like I did. Well, let me get my pen back if it'll come back. Okay, yeah. As I said, u squared is equal to sine squared x over 1 plus cosine x squared. Okay? Now, rewrite this as 1 minus cosine squared x over 1 plus cosine x squared. Well, this is 1 plus cosine x over times 1 minus cosine x. This is the part I didn't do. And this is 1 plus cosine x times 1 plus cosine x. These go out and you're left with 1 minus cosine x over 1 plus cosine x. And that's equal to u. U squared, right? Now let's multiply both sides of the equation by 1 minus cosine x. So you have u squared plus u squared cosine x is equal to 1 minus cosine x. Get all your u squareds together, all your cosine x's together, and that would be u squared cosine x plus cosine x is equal to 1 minus u squared. Okay, factor out the cosine x, and you get u squared plus 1 minus u squared, then divide both sides. Cosine x is equal to 1 minus u squared over 1 plus u squared. I just rearranged the order. So that's how they got that. Okay. to get the sign, let's go back to this one and do sine x is equal to u times 1 plus cosine x. Okay? Plug in what cosine x here is u is 1 plus 1 minus u squared over 1 plus u squared. And this would be u times 1 plus u squared over 1 plus u squared plus 1 minus u squared over 1 plus u squared. Okay? Combine, add these things together, and you get 2u over 1 plus u squared. And that's what the sine is. Sine x is 2u over 1 plus u squared. All right. Now, those two were relatively easy. Okay. How they get this one is a completely different thing. They use the tangent thing here. And so, all right, to go on a race, we got those two. I need more room to write. So they say tangent of x over 2 is equal to u. So x over 2 is equal to the inverse tangent of u. And then multiply both sides by 2. So dx is equal to, and then go to a table. This one I know we have. Derivative of inverse tangent. Arc tangent is u prime over 1 plus u squared. Okay? And this u prime is the du. 2 du over 1 plus u squared. So that's how they get that. Not through either one of the others, but through the tangent function. Okay? The other two they get through the sine and cosine. So what? Okay, here we have these three formulas. Really a pain in the neck looking formulas. And they don't do a single example with it. Why were we wasting all that, using all that time? They just do. Okay? Now, where would you use those? My guess, that would be on 55 through 61, the odds 55 through 61. Don't know that for sure, but my guess is that's where you would use these forms here. Because they don't show you any examples. And I think in the past I've just skipped them because they didn't show you any examples. I forgot that. Homework exercises in 8.7. This is, well, we got a little more time. Do number 3, it's a Calc Chat and Calc View. Number 5 is just a Calc Chat. Either 7 or 9 are both a Calc Chat. 11 is a Calc Chat. 13 is a Calc Chat. 15 is a Calc Chat and Calc View. 17 is a Calc Chat. Do either 15 or 17. They're both a Calc Chat. 15 is a Calc View. Do any of the odds 19 through 39. They're all at Calc Chat. Do any of the odds 41 to 47. They're all at Calc Chat. 41 is at Calc View. Do any of the odds 49 to 53, they're all at Calc Chat. None of them are Calc View. And then this is where you use those last few, I think, 55 through 61, and they're all at CalcChat. 63 is at CalcChat, 65 is at CalcChat if you are interested in that, and that's just exploring a concept. 67 is a work problem, 69 is a population problem, 71 is a volume problem. You can do any of those you want. They should all be at CalcChat. Now, improper integrals. What I think I'm going to do with this is we're going to do a slideshow on it, but that's all, because I don't think I asked any questions on this on the test, and I wasn't sure we're going to finish today, so I didn't get the test run off. But since we're not meeting next time, we don't have the extra day to work on it, so let me run down and run off the test for you. Chapter 8. Okay, I see it in here. Okay, this is it, I think. Yeah, that's it. Okay. Because the next chapter after this is 9, which we don't. Yeah, 9 is Infinite Series. Okay, so let me run. This is probably going to eat just about all the time we have left. I'm going to run off copies. And how many do I need? 1, 2, 3, 4, 5, 6, 7, 8, 12 copies. So let me run down, make the 12 copies. When I come back, I'll give them to you. That way you'll have something to do over the 4th of July weekend, and you won't be so disappointed that you have no calculus on Wednesday. So this